lecture accompanying the slides for Chapter 8 on the topic of rotational motion from Hewitt, 12th edition. All right, let's get into the topics. So in this chapter, we're going to discuss things moving in circles. That's going to involve circular motion, something called rotational inertia, which is really rotational mass, the concept of torque, which is like rotational force, something called the center of mass and the center of gravity, which are usually interchangeable terms, centripetal force, centrifugal force, what's the difference between the two, a rotating reference frame, simulated gravity, finally angular momentum, and how angular momentum is conserved, just like normal momentum. Okay? All right, well, let's get into it. Okay, so circular motion. When an object turns around an internal axis, like an axle, it is undergoing circular motion or rotation, like a Ferris wheel, or a merry-go-round, or a wheel on a car. Circular motion is characterized by two kinds of speed: tangential, which is linear speed, and rotational or circular speed. Okay? So there's two types of speed. They have different units, they're different quantities. So for example, if I draw a circle, and then we imagine that that circle is spinning in the counterclockwise direction, and I look at some point along the perimeter of that circle, that point would have a tangential or linear speed, v. Whereas the whole object has a circular speed. So v is in meters per second, but then the circular speed, which we represent as omega, so a Greek letter kind of serving the purpose of v, is actually in degrees per second or radians per second. So it's an angular measurement per time as opposed to an actual physical distance measurement per time. Okay? So a very important difference between the two. Notice that omega also doesn't correspond to a single point along our spinning wheel or rotating object. Instead, omega, the circular or rotational speed, encompasses the entire rotating object. So it describes the entire rotating object rather than a single point. All right? So let's get more into that. So what is tangential speed? The distance traveled by a point on the rotating object divided by the time taken to travel that distance is called tangential speed. It is no different than defining any type of speed, displacement over time. It's just that here the displacement is certainly some segment of a circle. Okay? Points closer to the circumference have a higher tangential speed than points closer to the center. Okay? Case in point, bugs on a turntable. All right? This bug may be fast, but this bug is faster. Is it twice as fast? Well, is it twice as far from the center? All right? If it is twice as far from the center, by the way, it would be twice as fast. So there you go. Okay? So, excuse me. That is tangential speed. All right? I'm not calling it tangential velocity because, of course, the actual direction of that velocity is changing as the bug or object completes a circle. The speed, the magnitude, could be unchanging. Now, it could be changing as well if the turntable is slowing down or speeding up, but we can think of a simple case where it's spinning at a constant rate, right? Where that blue arrow represents a steady rotational rate. All right? By the way, these green arrows are none other than the displacements that I've mentioned. All right? So, on the other hand, rotational speed, angular speed, is the number of rotations or revolutions per unit time. So both types of speed are per unit time, but rotational speed, represented by the Greek letter omega, describes all parts of a rigid merry-go-round or turntable turning about the axis, okay? Because the whole thing must turn in the same amount of time. It's not like some parts of the turntable or merry-go-round or car wheel can lag behind other parts. The whole object must make a full rotation in the same amount of time. That's why omega, unlike v, describes the entire object. Because clearly, v doesn't, because points close to the circumference are moving faster than points closer to the center or the axis of rotation. All right? So, to reiterate, all parts have the same rotational speed. Not all parts have the same tangential speed. Tangential speed is part specific. Rotational speed describes the whole rotating object. In fact, Tangential speed can be found if you know rotating speed, and it's found using this very important formula. V equals r omega. This tells us that the further you are from the center, the faster your tangential speed, because r is the distance from the axis of rotation. Going back to this figure here, this would be r, all right? And then, of course, we have this would be v, which would be equal to omega r. Where would I put omega on a figure like this? Well, I like to put omega up near the cartoonish arrow representing the spin. So omega would go right up here to denote that it applies to the entire object. Okay? Okay. So again, tangential speed is radius times angular speed. All right. A ladybug sits halfway between the rotational axis and the outer edge of the turntable. When the turntable has a rotational speed of 20 RPM and the bug has a tangential speed of 2 centimeters per second, what will be the rotational and tangential speed of her friend, who sits at the outer edge? Okay? Well, what is it going to be for tangential speed if she's on the outer edge? Twice as fast. Okay? Because the radius is twice as big, but the angular speed is unchanged. Okay, so far we've seen an important definition or two definitions of linear speed and rotational speed. Okay, now we're going to move into some other material. We're going to essentially move from kinematics of rotation into Newton's laws of rotation. And to do so, we need to define mass. Okay. And you might say, well, we've already defined mass. It's measured in kilograms. And another word for mass is inertia. Okay? Well, that's all fine if you're moving in a straight line. But if you're spinning, then inertia is fundamentally different. And we have to define something called rotational inertia. Okay? What is it? An object rotating about an axis tends to remain rotating about the same axis at the same rotational speed unless interfered with by some external influence. Okay? That sounds a lot like Newton's first law, because it is. This is Newton's first law in rotation form. Okay? Furthermore, the property of an object to resist changes in its rotational state of motion is called its rotational inertia, just like its translational, or another synonym, linear inertia, which we've been talking about up to this point. Rotational inertia is represented by the uppercase letter I. That's its variable, okay? Just like we tend to use the variable m to denote mass, or in other words, linear inertia. Okay? What does rotational inertia depend upon? Well, it definitely depends upon mass, so it has that in common with plain old garden variety linear inertia. Okay? But it also depends on the distribution of the mass. Well, that's fundamentally different and inherently more complex. All right? And specifically, it depends on the distribution of mass around the axis of rotation. Okay? Now, we actually have some common intuition based on how we interact with everyday items. For example, the greater the distance between an object's mass concentration and the axis, the greater the rotational inertia. It is easy to rotate this arrangement of weights and supporting beam as opposed to this orientation or distribution of weights and supporting beam. Why is it more difficult to rotate the second case? Because the weights are further away. Having them further away means that the moment of inertia of the overall object, beam plus 2 weights, is greater, despite the actual number of kilograms remaining constant. Okay? So that's the idea. That's the idea of rotational inertia. You don't just need to know how much of something there is, you also need to know where it's located relative to a particular axis of rotation. Well, it's probably whatever axis of rotation is currently in play. All right? In this case, the axis of rotation, would be coming out of the board, right? It'd be like this. Okay? Continued. The greater the rotational inertia, the harder it is to change its rotational state. A tightrope walker carries a long pole that has a high rotational inertia, so it does not easily rotate. That very long pole, although it may seem unwieldy, is hard to rotate. That means it's going to accelerate slowly. That means the tightrope walker has time to apply a good deal of force to get the pole back to a horizontal position, but importantly, has time to do so. All right? So that reduced rotational rate of the long pole is key for tightrope walking because it moves slow. Okay? Okay, so it effectively keeps the tightrope walker stable, but only because the tightrope walker is a dynamic system that can correct for itself because it's a human being. Okay, so furthermore, we can take a single object without changing it in any way, unlike the weight and supporting beam, and instead just consider rotating it in different ways, like a pencil, because a pencil has 3 unique axes. It is not the same exactly in any of those 3 axes, although it is pretty close to the same along its radially symmetric axis. So in other words, it's like a cylinder, okay? But a cell phone, on the other hand, is a rectangular solid where all 3 of the axes are distinct, okay? Does that make sense? How, it's not as thick as it is wide, and it's not as wide as it is long, okay? But let's consider the pencil. So the pencil is easy to rotate about an axis passing through it the long ways, okay? It is very easy essentially to roll it. That'd be this case here, okay? That's because it has very little rotational inertia in that direction because all the mass is very close to the actual axis of rotation denoted by the dotted line. On the other hand, it is harder, not particularly hard because it's a light item, but it is harder to rotate about an axis that passes through its center because now we have mass, some mass, right? If you think of little pieces of mass, this pencil being composed of an infinite number of little pieces of mass, we have some mass that's further away from the axis. That mass is harder to rotate, okay? We'll talk about how that relates directly to the idea of torque and levers in just a minute if you're starting to think in that direction. And of course, the hardest way, or perhaps it's not of course, but I'd like to make it clear that the hardest way to rotate the pencil would be around one far end, because now we have mass that's even further away from the axis of rotation. Okay? Didn't change the pencil at all, only changed how we rotated it and found 3 unique moments of inertia for this object. Okay? So do note that moment of inertia is mass distribution dependent, but that's mass distribution dependent relative to a particular axis of rotation. You change the axis of rotation even without making any physical changes to the object, and you still have a new distribution, right? These 3 distributions are all different. Okay? Now, perhaps the most dramatic example of this is just comparing between everyday rolling objects and thinking about which ones roll the easiest, okay? So we have here some common objects and their rotational inertias in formula form. A pendulum has the largest moment of inertia there is, and we call it a simple pendulum because all of its mass is assumed to be located in the yellow ball at the end of a massless string, and its moment of inertia is mr squared. That is the hardest thing to rotate because all of its mass is a maximum distance r away from the axis of rotation denoted here as that line that is meant to be 3D, in other words, coming in and out of the screen. Okay? Now it turns out that a hoop has an identical moment of inertia. Why is that? Well, because the hoop might as well just be a pendulum for the purposes of physics. Because here, the pendulum had all of its mass located at a distance of 1 radii away. So does the hoop. Sure, the hoop has it distributed around in a circle, whereas the pendulum has it all in one place. But for rotation, it doesn't matter. It doesn't matter if it's distributed in a circle or not. It only matters that it is all the same distance away from the axis. So the hoop and the simple pendulum have identical moments of inertia, and they both have the biggest moment of inertia that is possible for any mass distribution. Now, look at the form. The form is mr squared. that is always the form of moments of inertia. That tells us that moments of inertia are proportional to mass m and proportional to radius r squared. Okay, so I is directly proportional to mass and proportional to the square of the radius. That's all I need to know. Now, different shapes have different values in front of that mr squared. So far, we've just seen the two maximum cases, but look at the next one, okay? If we have a hoop and we're rotating it where some of the mass now is actually right on the axis of rotation, right? Same object, but different axis. Now we end up with 1/2 mr squared. What about a stick? If I rotate a stick about one end, I have 1/3 ml squared. L is still playing the same role as R, but since this is a stick, it makes more sense to refer to L for length than R for radius. If on the other hand, I rotate a stick about its center, well, that's easier to rotate, and now its moment of inertia is 1/12. See how 1/12 is smaller than 1/3, indicative of the fact that the stick is easier to rotate if we rotate it about its center? Common sense, consistent with what we talked about in previous slides. Other common shapes, the cylinder is 1/2, and the sphere is 2/5 mr squared. All of these values can be found directly through integral calculus. Okay? So, a hoop and a disc are released from the top of an incline at the same time. Which one will reach the bottom first? Okay? Well, it's the one that has the smaller moment of inertia, because the object with a smaller moment of inertia is easier to move from rest. It resists changes in its motion less. Remember the definition of inertia. And which of one of these two shapes has the smaller moment of inertia? The disc, of course. Okay? The disc has a moment of inertia of 1/2 mr squared. The hoop, on the other hand, has a moment of inertia of mr squared. So mr squared for the hoop, 1/2 mr squared for the disc. Thus, the disc resists changes in its motion less. Thus, the disc is able to accelerate at a greater rate. Thus, the disc arrives at the bottom first. Okay? The disc is faster. Okay, so a major player in talking about the dynamics of rotation is the idea of force. But I meant to say torque. But really, torque is rotational force, hence the slip up. Okay, so let's get into the idea of torque. So torque is the tendency of a force to cause rotation. Okay, now it doesn't have the same units as force. Torque, often represented by the Greek letter tau, kind of drawn like a curly T, has units of Newton meters, the same units as work. Okay, although torque is a vector and work is not, so they are absolutely physically distinct quantities. They do, however, have the same dimensions. Okay, torque depends upon three factors: the magnitude of the force, the direction of that force relative to a rotational axis, and the location of that force relative to a rotation axis. Okay, so just like with moment of inertia, you should, or maybe I should say, along with moment of inertia, you should start to see a trend here. When we talk about rotation, we have a lot of things we have to consider that we wouldn't have had to for translation, in other words, linear motion. Now we have to worry about where things are and the angles of everything. There's just more bookkeeping when it comes to rotation. Okay? That means that the effects can be wonderfully subtle and amazing, okay, such as gyroscopic motion, but is more to wrap your head around. All right, let's get more into torque. So, the formula for torque is lever arm multiplied by force. This is where we get that idea of Newton and meter, so you can see where the units come from. Okay, and the lever arm itself depends upon the force and the direction. Okay, so that's where the direction comes up, is in the concept of the lever arm. All right, so location and direction gives the lever arm. All right, let's talk about how then we would visualize the lever arm using the idea of vectors and components and right triangles. Okay, so the first picture, the lever arm is less than the length of the handle because of the direction of the force. Notice that I consider a force, in this case the hand is applying a force in the direction of the arm, right there, and that force is continued down here. This continuation of the force is called the line of action. We continue it down until we can make a 90-degree angle. Thus, the other side of that right triangle, because there of course is the 90 degrees making the right triangle, is the lever arm. So only one side of that right triangle is the lever arm. Here, the lever arm is shorter than the length of the wrench. The actual length of the wrench will be the hypotenuse of the triangle. All right? On the other hand, if we apply the force perpendicular to the handle, now the entire handle becomes the lever arm. We don't have to worry about just taking a component or one side of a right triangle. The hypotenuse is, well, just the whole length. Our triangle has just been compressed to a single line. Okay? So why did that happen again? It happened because in the first case, our force was not perpendicular to the handle. In the second case, the force is perpendicular to the handle. Thus, the entire lever arm, or I should say the entire handle, is the lever arm. That tells us something. It tells us that the way to maximize torque is to apply a force perpendicular to the handle. Okay? Now, maybe not every situation is a handle, but it's always some physical displacement. So whatever is because here this wrench here, or this nut rather, is the axis of rotation. Okay? And so then this essentially is the radius. So if we want the entire radius to be the lever arm, we have to make sure that our force is perpendicular to that radius. Okay? Now, furthermore, we could make our handle longer by having some sort of extender put on it. In that case, we apply our force perpendicular again, as we did in the second case, but since our length is even longer, our torque has gotten even bigger. Okay? So a long wrench supplies more torque. This would allow us to turn the nut tighter, loosen it if it was stuck, and so on. Suppose the girl on the left, we're going to look at an example of lever arms in the context of balancing things like with a teeter-totter. Suppose the girl on the left suddenly is handed a bag of apples weighing 50 newtons. Where should she sit in order to balance, assuming the boy does not move? Okay? So currently the situation is balanced at the boy's current location. Okay? But she now is going to become heavier. If she's going to become heavier, where does she need to move? Okay? So think about her current situation. All right? So we have 1 meter from the pivot, 1.5 from the pivot, 2 from the pivot, and 2.5 from the pivot. Okay? She's currently 3 meters from the pivot. All right? So let's think about what's gone on here. She should exert the same torque as before. All right? So she was 3 meters and it was left off, but her weight was 250 newtons. Thus, her torque was 3 times 250, which is 750. However, if she was handed an extra 50 newtons, then she's going to be heavier, okay? So in this case, she would have to then move closer to the pivot, but not that much more, because she's only increased her weight slightly, and so she'd have to move 2.5 meters from the pivot instead of the 3 meters that she was currently located at, or previously located at. Okay? So that's the concept of torque. All right, you'll get more examples in the homework as well. All right, so moving on to the concepts of center of mass and center of gravity. All right, now again, these are basically interchangeable, but let's explain what they are. So center of mass is the average position of all the mass that makes up the object. Center of gravity is the average position of the weight distribution. Since weight and mass are proportional, center of gravity and center of mass usually refer to the same point of an object. They only wouldn't if gravitational force varies over the volume of an object, which it definitely doesn't for anything small. You know, you'd have to think of huge objects like planets, and in that case, then yeah, say for example, the gravitational force of the sun would vary slightly over the entire volume of Earth. Okay? But that is really the only time you would have an appreciable difference between center of gravity and center of mass. For our purposes, they're always going to be the same point. It's just one is referring to a weight distribution and the other is, well, referring to a mass distribution since it is in its name. Okay? So Let's think about it. Now, if you are in Physics 10L, you've already seen a lab on this very concept. But to determine the center of gravity, you suspend the object from a point and draw a vertical line from the suspension point. Then you repeat that from another suspension point, and the center of gravity is where the two lines intersect. You can do more than two lines and further refine your crossing of points, because perhaps the third line doesn't cross exactly at the location of the other two, and then you can kind of have a center of that region is a better and more accurate measurement of your center of mass, okay? But you can just find the intersection of two lines, and that must be your center of mass, okay? And the idea of that is that there was holes in this object, so that it could be hung in different orientations, okay? And this thing that's hanging is just hanging straight down in the direction of gravity, all right? It's just a weight at the end of a string, okay? Furthermore, center of gravity has a nice connection to the idea of stability. The location of the center of gravity is important for stability. If we draw a line straight down from the center of gravity and it falls inside the base of an object, that object then is in stable equilibrium. It will balance. If it falls outside the base, it is unstable and it will accelerate and rotate, okay? Because there's nothing to stop it from rotating. So, right, Leaning Tower of Pisa, the center of gravity is still above the basically the foundation of the building. Thus, the tower is still stable, just tilted. Okay, so moving on to our next topic, centripetal force. Okay, so this is going to relate nicely to the ideas of linear motion and rotational motion that we opened the slides with. So any force directed towards a fixed center is called centripetal force. Okay, centripetal force actually means center seeking, or towards the center. So that's why we know that the force always points towards the center. So this would be FC for centripetal. Example, to whirl a tin can at the end of a string, you pull the string towards the center and exert a centripetal force to keep the can moving in a circle. Of course you do, right? You feel in your hand that you're having to pull on that string. So there's a tension here, all right? And then there's a tension here. The tension acting on the can is exactly equal in magnitude and opposite direction as the tension on the string where the string comes in contact with the hand, okay? However, these two tensions do not make a force pair because they're both acting on the string. It's just that they're equal in magnitude and opposite direction because the string is assumed to be massless. I bring that up because it's a good throwback to material we've seen before. But what's new is that now we have a new name. We actually call the tension acting on the can the centripetal force, okay? Why do we call it that? Well, we call it the centripetal force because it is the force that creates circular motion, okay? A centripetal force can be created by common forces like tension, normal force, gravity, friction. Basically, all of the contact or non-contact forces we've discussed so far are capable of being a centripetal force in the right circumstance. What's the right circumstance? Well, when they're causing an object to turn in a circle. As simple as that, okay? Usually causing the object to turn in a circle at a constant speed, but it need not be a constant speed, okay? But most of the time, that's what we're referring to. Spinning something at a constant rate, going around a turn at a constant rate. All of those have a centripetal force, okay? So centripetal forces allow things to turn, but of course they do. You can't turn without pulling a force to pull that object into the turn, right? We're pulling the object into the turn. That's why the force points towards the center. We're pulling the can kind of in this way, thus causing it to turn along the dotted line. Okay, hopefully that makes sense. I'm stressing it because we're soon going to talk about another force that you probably heard of called the centrifugal force. And it's very important to understand the difference, but we'll get there in just a moment. Okay, so the centripetal force depends on a couple things. It depends on the mass of the object. So in the previous slide, that would have been the mass of the can. It depends on the tangential speed. That's just how fast the can is moving. Notice that's tangential speed, linear speed, not rotational speed. So it's the speed that is point dependent. Okay, so it would be wherever the can is located relative to the axis of rotation, and it's the speed that's measured in meters per second, not radians per second. Okay, it's the one represented by a v, not an omega. Okay, and the radius of the circle r. All right, so again that would be m, v, and r. Okay, so in equation form, it's mass times tangential speed divided by radius. and his tangential speed squared. So that what that looks like then is Fc equals mv squared over r. That's always the formula for calculating centripetal force. Okay, that's the force that you need to create through some process, such as tension, in order to turn something in a circle. It's as simple as that. Okay? So, when a car rounds a curve, the centripetal force prevents it from skidding off the road. Okay? There is the centripetal force. If the road is wet, or if the car is going too fast, the centripetal force might be insufficient to prevent skidding. Okay? In that case, the force cannot actually cause a circle of the desired radius, right? So essentially, it's the car then it will be moving out to a larger radius circle, but the problem is that probably the edge of the road or the embankment or something is in the way, okay? So it can't just kind of naturally glide out to that bigger circle, all right? That's the idea. There needs the centripetal force, since it's dependent on the radius. Well, to maintain a particular radius, you got to have enough force to do so. What would actually create the centripetal force for the car? Well, one thing could be friction. So the centripetal force could be entirely from friction. But also think about a banked turn. If the turn is banked, then some of the actual normal force is in the direction of the centripetal force. Because from a side view, the car would look like this, and the normal force would be pointing in this direction, actually in towards the circle, because this is R, towards the center of the circle. So a component of the normal force, FNR, is actually pointing inwards. So could some of the friction, okay? So, suppose you double the speed at which you round a bend in the curve. By what factor must the centripetal force change to prevent you from skidding? Think about the formula. What is the proportionality between Fc and V? Okay, what is it? Is it direct proportionality? Nope, it's squared. That means that if you double the speed, you have to have 4 times the force. Okay, that's why it's important to consider how fast you're going into turns. There's not a lot of leeway there because it is a square relationship. Okay, 4 times the force is a lot more force. All right. So suppose you take a sharper turn than before and halve the radius. By what factor will the centripetal force need to change to prevent skidding? Okay, so remember the formula, Fc equals mv squared over r. If I cut r in half, how much bigger does my centripetal force have to be? Okay, I kind of gave away that it has to be bigger, so maybe we can eliminate 2 of the options. Make sure you're confident though. In this case, it's double, because you now have an inverse relationship between centripetal force and radius. Okay, it's not like the radius is squared. So doubling the radius just means, well, cutting the centripetal force in half, or cutting the radius in half means doubling the centripetal force. Okay? Okay, now centrifugal force. What is that? Well, it's actually not a real force. Let me elaborate on that. Although centripetal force is center directed, an occupant inside a rotating system seems to experience an outward force. This apparent outward force is called centripetal force. Centripetal force means center fleeing or away from the center. So the names are centripetal, center seeking, centrifugal, center fleeing. Okay? Now, centripetal force is the actual force necessary to maintain circular motion, rotation. Okay? Centrifugal force is not a real force. It is an apparent force that is experienced by an occupant in that rotating system because that occupant has their own inertia, follows Newton's first law, wants to continue in a straight line. The surrounding environment of the rotating system prevents them from continuing in a straight line. Thus, they seem like they're being flung out of the circle. They seem to experience a force outward. That's no different than if you're in a car and someone slams on the brakes, you seem to experience a force that throws you forward. But there's no real force that throws you forward in a braking car. There's just your own inertia. You want to continue in motion in the direction and velocity you are traveling at, direction and speed. Okay? Same for a turn. You want to keep going straight. The seat in a car prevents you from going straight, but that makes you feel like you're getting flung out of the circle. Okay? So centrifugal force is just a perceived apparent force, not a real force, because all forces that are measured in rotating systems, which are accelerating systems, are not true forces. They're always apparent forces. Okay? Okay. So, common misconception. It is a common misconception that a centrifugal force pulls outward an object, that it is a true external force and not just a perceived apparent force. Well, example. If the string breaks in the can that we considered above, or a few slides back, that was being rotated due to a true, real centripetal force that was created by tension in that case, well, if the string breaks, the object doesn't move outward. In fact, it continues in a straight line path because there was never a force acting on it outward. Okay? Newton's first law. It has to continue in the direction it was moving because now there's no more force acting on it. Okay? So the fact that the object moves in a straight line if the string is broken is a testament to the fact that the centrifugal force was never there, that it was just an apparent force. Okay? So, here's the technical term for why the centrifugal force is an apparent force. The centrifugal force is in a rotating reference frame is a force in its own right, as real as any other force, for example, gravity. Okay? The bug at the bottom of the can experiences a pull towards the bottom of the can, a centrifugal force, right? So that bug inside the can feels like, oh, I can walk around. It's like artificial gravity, right? So for all intents and purposes, if there was no windows in this can, this was a little room for the bug would think that down is this direction, right? And it might as well be, as long as the can keeps spinning, okay? Now, from the outside, we can say, oh, well, that only appears to be down to the bug because the bug is in a rotating reference frame, okay? But that has the advantage of looking from the exterior into the system. From the interior of the system, it does appear to be a real force, okay? But it only appears to be that real force, okay? And that really tells us that our reference frame, our perception of what we're experiencing is very important. In fact, that led to one of the keystone theories of the 20th century, Einstein's general theory of relativity, that says that it is impossible to distinguish between gravity and artificial gravity like this, like the centrifugal force. Okay? So, fascinating stuff. But regardless, we can, if we have the ability to distinguish between the systems, say, oh, well, one is an apparent force because it's in a rotating reference frame, and the other one, centripetal force, is a real force because it is in a non-rotating reference frame. Because, of course, the person holding the can is not rotating. They're just standing on the ground. But then, isn't the Earth rotating? There's some issues, right? But that's the thing, right? How accurate do you want to be with considering your reference frame? All right? So, continuing on with ideas, simulated gravity. So the centrifugal force can be used to simulate gravity in space stations of the future. Okay, maybe you've seen this in sci-fi movies, big spinning space stations. By spinning the space station, occupants could experience a centrifugal force, simulated gravity similar to the bug in the can. Okay, so for them, down would be the direction of out, because for them, the centrifugal force would seem entirely real. They'd drop objects, they'd move in that direction, it would seem like gravity. Okay? The simulated acceleration due to gravity, g, that's our 9.8 meters per second squared, what we are used to as humans evolving on planet Earth. A space station must, for example, have a radius of about 1 kilometer and rotate at a speed of about 1 revolution per minute. So that would be one combination of size and speed that would achieve an artificial gravity space station. Okay, so big space station, right? Way bigger than anything we have so far, which is just the International Space Station, but a kilometer across, okay, 2 kilometers across because the radius is 1 kilometer, and a pretty fast speed of a revolution per minute. So you can think about how great the tangential speed would be in that case. It'd actually be quite large, okay? And then the simulated gravity of G would only apply to people that were on the outside of the ring, right? That's why the ring is drawn without anything on the inside, because the gravity would vary with radius, so you couldn't use the whole space station. You'd only be able to have the outside ring as usable, at least in terms of having just the right gravity. Well, artificial gravity. Okay? Let's get to our final topic. Okay? So, if you recall, we've talked about momentum, and it turns out there's also such a thing as angular momentum. It makes sense to kind of wrap up our chapter here. We're talking about angular momentum because we've talked about basically everything else rotational. Okay? And so we should talk about rotational, or also known as angular momentum. Okay? So the inertia of rotation of rotating objects is called angular momentum. This is analogous to the inertia of motion, which was momentum. Okay? Angular momentum is rotational inertia times angular velocity. Very similar to the way that linear momentum was mass times velocity, because recall before it was P for linear momentum was mv. That was just mass times velocity. Well, now for angular momentum it's L, and we know it's I for rotational inertia, and then angular velocity is omega. Okay? So then what are the units? Well, I has units of kilogram meter squared. Omega has units of radians per second. Radians aren't a unit, they're just a kind of a tracking tool. So then the dimensions or units of angular momentum would be kilogram meter squared per second. All right? And that's in contrast to linear momentum, which was just kilogram meters per second. Okay? So look at the difference. Angular momentum just has an extra meter. That's all that distinguishes one from the other. Okay? But angular momentum refers to the idea that things that are spinning want to keep spinning. Okay? Just like momentum was the idea that objects that are in motion want to continue in motion. All right? And remember that was the fine line to distinguish between momentum and inertia, because inertia applies to things that are at rest as well as motion. And inertia, for at least in the linear case, just had units of kilograms. Momentum was conserved in collisions and had different units and only applied to objects in motion. Likewise for angular momentum. All right? It's useful for collisions, and it only applies to things that are moving. Okay? For an object that is small compared with the radial distance to its axis, the magnitude of angular momentum equals mass tangential speed times radius. All right? So this is analogous to the magnitude of linear momentum, which is just mass times speed. All right? So in other words, we have mass tangential speed times radius. So that would be mvr. Okay? Now this applies really nicely to things that don't have a big mass distribution. So if we wanted the angular momentum of a disk or a sphere, we could not use mvr. But for our pendulum or ring or hoop, it would work quite well to use mvr. All right? So we have to be careful about what our shape is. Again, rotational motion is a little bit more complex, right? So whirling a ball at the end of a long string or planets going around the sun work very well to describe angular momentum as mvr. Okay? What's nice about that is we don't have to worry about the moment of inertia. Notice there's no I here. And we don't even have to worry about omega, the rotational speed. We just have mvr. Rather easy things to calculate and understand. Okay? So, how do we deal with the conservation of angular momentum? Well, an external net torque is required to change the angular momentum of an object, just like an external net force was required to change the translational or linear momentum of a system. So rotational versions of Newton's first law. An object or system of objects will maintain its angular momentum unless acted upon by an external net torque. Notice all we've done here is replace momentum with angular momentum and replace external net force with external net torque. Okay? So there's a direct analogy that took us from linear systems to rotational systems. Now, I said it's useful for collisions, and certainly we can have cases of collisions and angular momentum, like an asteroid crashing into a planet and maybe changing the length of day of that planet subtly. But really one of the better systems to think about for angular momentum is just changing the shape of an object. I call this the ice skater example, right? An ice skater pulls their arms in, they've changed their radius, and their velocity goes up, okay? Well, let's think about, instead of ice skater, let's think about a can. Suppose you are swirling a can around and suddenly decide to pull the rope in halfway. By what factor will the speed of the can change? Okay, so think about the fact that there is no net external torque acting on the system. Pulling the can in is internal to the system. Okay, so external net torque is 0. Thus, angular momentum initial must equal angular momentum final, which means that mvr must equal mvr. F for final, I for initial. Notice I didn't put any subscripts on the m because the m didn't change. The mass of the system remained unchanged. It could have changed, but it didn't. Okay? Instead, the only thing that changed was r, and then v had to change to compensate. So what's it going to be? Double. All right? And again, we're just using the formula mvr. Angular momentum equals mvr. Notice that the printed slide gives it to you in word form. I'm adding the equation form so you can see it both ways. Okay? So the law of conservation of angular momentum states, if no external net torque acts on a rotating system, the angular momentum of that system remains constant. This is absolutely analogous to the law of conservation of linear momentum, which, if you've forgotten, this is a great time to be reminded of it, which states that if no external force acts on a system, the total linear momentum of that system remains constant. Okay? So at this point, we have seen the 3 conservation laws of mechanics: conservation of energy, conservation of translational momentum, also known as linear momentum, and conservation of angular momentum. Those are the only 3 conservation laws of mechanics. Okay? So good. Check, check, check. Okay? So here's the other example I mentioned. In this case, this system is not well described using the MVR expression of angular momentum. Instead, we want to use L equals I omega. Why is that? Because not all the mass is distributed the full radius away. This person with their dumbbells has mass throughout their body, throughout their arms, and of course in their hands they have a lot of extra mass that can have a big effect because they're holding big heavy things in their hands. So when the man pulls the weights inward, his rotational speed increases. Why is that? Well, initially he had a large moment of inertia because it was difficult to rotate him. He had a lot of mass far away from his axis of rotation. Remember, that's the way to think about moment of inertia. The more mass far away from the axis, the bigger the moment of inertia, I. Thus, his omega was relatively small. Okay? He was spinning at a slow rate. But when he pulled his arms in, his moment of inertia dramatically decreased because it's proportional to r squared, and there was a lot of mass. All of a sudden, all that mass is pulled inwards, okay? Which means his omega, his rotational velocity, which describes his entire body, because remember, omega describes the object as a whole, not a single point on the object, unlike v, right? Tangential linear velocity. So omega, his whole body, starts to spin much faster, okay? So that's another case of conservation of angular momentum. So suppose by pulling the weights inward, the rotational inertia of the man reduces to half its value. By what factor would his angular velocity change? What's the relationship? Make sure you know this. It would simply double, right? It's a straightforward relationship. It's just one term multiplied by the other, okay? So it's I initial, omega initial equals I final, omega final, okay? If you double one, you have to cut the other in half. If you triple one, you have to cut the other by a third, okay? Or to a third. All right, thank you so much for watching this lecture video on rotational motion. Rotational motion is a big, complex topic, potentially. Obviously, we are just touching on it in this class, but make sure you review it a bit because it is one that can throw you for a bit of a loop initially, okay? All right, so please stay tuned this week for another lecture on the topic of gravity and orbits.